Let's make an example for the matrix diagonalization. Okay, matrix diagonalization example. And we will use the same mass spring damping system. Okay, so we have y prime equals to ay plus g. You have the a is 0, -2, 1, 3. G is 0, 1, 10 e to the -2t. We already got the homogeneous solution so that we know what is our diagonal matrices. Well, we construct with all the eigenvalues. So we have eigenvalue -1, eigenvalue and -2. Then we have our T, which is our eigenvector model matrices. So it will be 1, -1, which is associated with the eigenvalue -1. We have 1, -2, which is associated with eigenvalue -2. Okay. Then we assume for the matrix diagonalization, we have to assume first our general solution will look like TZ, right? So our T is our model matrices. Then we will solve what is the Z part, right? And we know that ZIT is equals to e to the lambda IT, integral e to the negative lambda IT minus HIT dt plus some constant. If you involve this constant, it will be general solutions. If you don't include this constant, then it will be particular solution. Since we are trying to solve what is the general solution, so we will include this part. Okay, the HIT will be equals to T inverse times G. Okay, this is actually HT here. T inverse is what? T inverse will be inverse of this matrices. You can use either the Gauss-Jordan elimination, or you can use the transport matrices. We will just show the result here. You can do later by yourself. So the T inverse of this model matrices will be 2, -1, 1, -1. Okay. Then HT will be T inverse G. It will be 2, -1, 1, -1. G will be 0, 10 to the e to the -2t. Okay. And that is in the end is 10, -10 e to the -2t. So that is UHTs. Then you will know what is UH1, what is UH2. So when lambda equals -1, when lambda 1 equals to -1, then you have Z1T. We just need to input all the variables we already know in these equations. So that will be e to the -t, since lambda 1 equals -1, times the integral e to dt, negative h1t will be 10 to the e to the -2t dt plus c1. Okay. Then we get e to the -t times -10 e to the -t plus c1. So that is when lambda 1 equals to -1. Then what is our lambda equals to -2? So when lambda 2 equals -2, the z2t will be equals to e to the -2t, integral e to the 2t, -10 e to the -2t, dt plus c2. And that is e to the -2t, -10t plus c2. So you already got your z1 and z2, you know what is your z. And you know that the final solution will look like T, Z. So you know what is UT is your model matrix, which is 1, -1, 1, -2. The Z will be Z1 and Z2, -10 e to the -2t plus C1 e to the -t, -10 t e to the -2t plus C2 e to the -2t. Okay? So you know why. You also know here has some constants. So this is your general solutions if you don't have any initial value problem. However, you know what is your initial value. So y0 will be equals to 0, -5. Then you can input this initial value into the general solutions and get what is your C1 and C2. Okay, so the final solution, the exact solution, or you can say the unique solution of this problem is when C2 equals 5, C1 equals to 5, so that your y will be equals to -5 e to the -2t minus 10t e to the -2t plus 5 e to the -t. The second will be 20t e to the -2t minus 5 e to the -t. Okay, so that is your final solution. It should be exactly the same as how we solve for the undetermined coefficient. And one thing to note that whenever you are trying to input the initial value problem has to be applied for the general solutions, okay? Have to apply to the general solution, not the homogeneous solution only, okay?